Welcome back to this lecture number 14. Sorry, lecture number 18. We are continuing to study the splines, cubic splines to be more precise. Let me start sharing my slides. I hope you can all see them now. All right. Okay, so we have this definition of cubic spline. Suppose we have a function f which is defined on a closed and bounded interval AB, and it's taking values inside the real numbers R, and we have these n plus 1 nodes which are x0, x1, x2 and so on, which are written in the increasing order. These are all distinct, of course. A cubic spline interpolant, which we denote by capital S for our function f, is a function which satisfies, first of all, that on each subinterval xj to xj plus 1, it's given by a cubic polynomial, and these cubic polynomials have the property that they of course interpolate the function on these 2 points xj and xj plus 1. But not just that the sj and sj plus 1 happen to be the same on the common point, their derivatives and the double derivatives are also the same. This is what we have for the spline that is given by cubics. And one point here is that often we will not have the finer derivative property for the points which are inside. We will put some boundary conditions. So the one of the boundary conditions which is very natural and that's why it's called a natural boundary condition, which is that the double derivative at both the endpoints are 0. The external endpoints, the double derivatives are both 0. Or if you have information about the derivative of the function at those endpoints, then we clamp our spline by declaring that the derivative at x0 and the derivative at xn be equal to the derivative of the function f at those 2 points respectively. This is what we have. So we have cubic spline with the natural boundary condition or the clamped boundary condition, and it's more common, of course, to have natural cubic splines than the clamped ones because information about derivative at various points may not always be available. What we would have is that we would have some nodes, and we would have the information about the function at those nodes, but we may not always have derivatives, the information about the derivatives. But whenever this information is available, we will use it and get clamped cubic splines because those will give us a better approximation for the function f on the interval AB that we are working with. Before we go on to the general construction on how these cubic splines are constructed, we will see an example which will illustrate the general case. So we start with the data. We start with these 3 points. So we have x0 is 1, x0 is 1, x1 is 2, and x2 is 3. And the function values at these points are 2, 3, and 5 respectively. We want to construct a natural cubic spline. So our double derivative is going to give you the 0 value at the endpoints which are 1 and 3 here, and we have 2 as the intermediate point. So we are going to have 2 cubics. There will be this cubic which we will write as A0 plus B0 into x minus 1, C0 into x minus 1 square plus D0 into x minus 1 cube. We have this cubic on the interval 1 to 2. And we have this another cubic S1, which is written in terms of the powers of x minus 2 on the interval 2, 3. So this is the these are the 2 cubics that we are going to have, and we will try to interpolate our function using these 2 cubics. So what are the conditions? Of course, you will have that S0 of 1 has to be the function value at 1. And S0 of 1 can be easily computed because we will simply put x equal to 1 in S0, and this highlighted term will go to 0. It will be equal to 0. So you get that as A0 has to be 2. So we have information about A0. Similarly, we will have information about A1. So out of these 8 constants that we have to compute, A0, B0, C0, D0, and then you have A1, B1, C1, D1. So out of these 8 constants, we have information about A0 and A1. Okay, that's good. Then we will also need that the first cubic polynomial on the second endpoint, or the point which is common between the two subintervals, its value has to be equal to the value of the function at 2. So the value of the function at 2 is 3, and so S0 of 2 has to be 3. So we will get that A0 plus B0 plus C0 plus D0 is 3. Okay, we know the value of A0. We have now one equation for 3 unknowns, B0, C0, D0. Similarly, S1, 3, which is the second cubic spline, second cubic polynomial at the final third point, the point x2. Its value is 5. So you have A1 plus B1 plus C1 plus D1 equal to 5. So we have once again another equation for 3 more unknowns. We right now have 6 unknowns and there are 2 equations. We also have that S0 prime equal to S1 prime at 2 and S0 double prime equal to S1 double prime at 2. Remember, we had 8 unknowns. Out of them, we had values determined for A0 and A1. So there are 6 unknowns now. We would typically need 6 equations to compute 6 unknowns. If we want to determine them uniquely, we already have one condition which is S0 of 2 equal to 3 and another condition which is S1 of 3 is 5. So we have 2 equations now for 6 unknowns, and so we would need 4 more equations. These are the 2 more equations, that S0 prime at 2 equal to S1 prime at 2 and S0 double prime at 2 equal to S1 double prime at 2. So we get these 2 equations. So we have B0 plus 2C0 plus 3D0 is B1 and 2C0 plus 6D0 equal to 2 times C1. Okay, so out of these 8 unknowns, we are left with 6 unknowns and there are now 4 equations. And once you put the boundary conditions, which are the S0 double prime at 1 equal to 0 and S0 1 double prime at 3 equal to 0, we get a collection of 6 equations. So we have 6 equations, 6 unknowns, and putting them in various values, we would get that. So here you already see that C0 has to be 0. 2C1 plus 6D1 equal to 0, it gives you some value for D1 in terms of C1. If you put it back in the earlier equations, here you can put it back and you would have some equation in terms of B1 and C1, and C0 is 0. So this gives you just B0 plus D0 equal to 3. And here you have B0 plus 3D0 equal to B1. And finally, you have 2C0 plus 6D0 equal to 2C1. All these conditions can be put together. And when you solve these equations, we get this particular spline. So we have 2 cubics. We have the S0, which is 2 plus 3 by 4 into x minus 1 plus 1 by 4 into x minus 1 cube. Remember, C0 is 0. So we will have only A0, which is 2. A1, A0 is 2, B0 is 3 by 4, and D0, which is 1 by 4. And then you have the equation for the second cubic, which is 3 plus 3 by 2 x minus 2 plus 3 by 4 x minus 2 square minus 1 by 4 x minus 2 cube. So together with the boundary conditions, we have a total 6 equations for 6 unknowns, but of course we have to argue that these 6 equations do give us a unique solution, and that needs some proof. We will see how to come to that. So let's go to the construction of a general cubic spline. Okay, so as the example demonstrates, there we had 2 cubics and so we needed 8 constants that were to be determined. So if you have a cubic spline and your interval is divided into n sub-intervals, then you are going to need 4n constants in all. Okay, and out of these 4n constants, we will see one by one how to go on determining the constants. So first of all, we have the cubic spline interpolant for a given function f, and the conditions will be applied to this particular cubic that we have here in the blue color, Sj, which will be given by Aj, Bj, Cj, and Dj. Aj will be the constant term, Bj will be the coefficient of x minus xj, Cj will be the coefficient of square of x minus xj, and dj will be the coefficient of the cube of x minus xj. What happens is that when you put x equal to xj in sj, you will get that the sj of xj, which has to be the function value at xj, has to be equal to aj. So aj's are all determined straight away. So out of the 4n constants that were to be determined, you have determined the n constants right away. Okay. And moreover, you also know that sj of xj plus 1. So your polynomial, cubic polynomial sj is valid from xj to xj plus 1. So on the next endpoint, which is xj plus 1, we will have that its value has to be s of j plus 1 at that point xj plus 1. And therefore, that has to be equal to a j plus 1, because that's what we have computed just now. So we get that aj plus 1 has to be aj, which is the constant term. So we are going to evaluate this blue polynomial on the point x equal to xj plus 1. And therefore we get aj plus 1 is aj plus bj into the difference of xj plus 1 and xj plus cj, the difference square, plus dj, the difference cube. Now this difference will keep coming again and again. So to ease the notation, what we are going to do is that we will simply write it by hj. Okay. So we will have a simpler looking equation, which is the same equation that we had earlier. So this simpler looking equation is aj plus 1 is aj plus bj hj plus cj hj square plus dj hj cube. Okay, this equation is valid for j equal to 0, 1, 2, 3 up to n minus 1, because we are looking at the points which are common. Okay, so you will of course have s0's value on x1, s1's value on x2, so on up to sn minus 1's value, sn minus 2's value on xn minus 1. We will of course have the sn minus 1's value on the last point, which is the xn point, and so we will actually have this equation valid for n terms 0 to n minus 1, but then we will have to declare that our an, right now we don't have an. Remember, we have the polynomials sj going from 0 to n minus 1, and we are talking about a j plus 1. So this a j plus 1 will occur when you have j equal to 0 will give you j plus 1 equal to 1, all the way up to a n minus 2 will give you j equal to n minus 2 will give you a n minus 1, which is the a constant term of the last polynomial. But we will define an. We will define an to be the function value at xn. And so we will have this valid, but we are going to mention it a little later. Okay, so let's remember that we have this equation number 1, which is the value of the sj and sj plus 1 on the common point of those two subintervals. Okay. Now we will look at the derivative. So we have the sj here. If you take the derivative of sj with respect to x, the constant term will be cancelled. You will simply have bj, and then you will have two terms which will have x minus xj as a factor. So when you compute the derivative and put x equal to xj, you are going to get only bj. So that tells you that bj, which is the derivative of sj at xj, it has to be the derivative of sj plus 1 at, so there is a small, I think I should put bj plus 1, which will be, so what I mean to have here is that bj is the derivative of the cubic polynomial sj at the point xj, and what we should have is that sj prime at xj plus 1 has to be equal to sj plus 1 prime at xj plus 1, because we are also demanding that the sj prime and sj plus 1 prime will have to agree on the point which is common. So that will give, indeed, that's what we have in the next equation, that b of j plus 1 is, so b of j plus 1 will come from here, sj plus 1 prime at xj plus 1, and the RHS that we have here should come from here. So therefore we should have bj plus 2 cj hj plus 3 dj hj square. I have told you just now how to compute the derivative of sj, And if you put for x the point xj plus 1, then we have xj plus 1 minus xj, which we have defined to be hj. And so you will have bj plus 1 equal to bj plus 2 cj hj plus 3 dj hj square. So we have one more set of equations. And the double derivative, once again, I think I have made a goof of here. So this should be split up into either two equations, or we have to give the indices correctly, but it will give you the final equation that's going to be correct, which is cj plus 1 equal to cj plus 3 dj hj. All right, so this is the particular, these are the sets of equations that we have. And now here we come, we will define an. So until here we had an minus 1. We had it only up to an minus 1. But similarly, we had this only up to bn minus 1. The equation 2 was only up to bn minus 1, and equation 3 was only up to cn minus 1. So we had a total of n minus 1 sets of equations for all these three types of equations. But now with the definition of an being made, which is f of xn equal to sxn, bn, which is the derivative at s of s at xn, which is going to be the Sn minus 1's derivative at xn, and 2cn, which is the double derivative at xn. With these definitions, we will have that these above three types of equations are valid for j equal to 0, 1 up to n minus 1. So you will have 3n equations. For each of the types, we have n equations. So we have 3n equations, and we have already determined the n coefficients, which are aj. So together we do seem to have 4n equations, but of course we have to, there are these two, bn equal to s prime xn and 2cn equal to s double prime xn. These are not really equations because we don't have these informations. Here we have the information about f of xn. That's an information that is given to us, but this information is not something given to us. So we will still need two more equations, and those are going to be the boundary conditions. But let's see what we can do with these equations at the moment. So equation 3 we see here is cj plus 1, which is cj plus 3 dj hj. Okay, hj is a non-zero quantity because all these xi are distinct. So I can divide throughout by hj, and then we can put cj on the other side. So we will have that dj can be solved in terms of cj, cj plus 1 and hj. Okay, so we will solve for dj and put these values back in equation 2, which is in front of us, and equation 1, which is a similar equation but for a's. So you will have aj plus 1 equal to aj plus bj hj plus cj hj square plus dj hj cube. There, that's where we put the value for dj in terms of cj plus 1, cj and hj. And that gives us these two equations. So we forget equations 1 and 2 for the moment, and we have these new equations 4 and 5. So we have taken care of one particular set of constants, which are the dj's, and we have now these equations for aj, bj and cj, and hj are known to us. Hj's are simply the xj plus 1 minus xj. We also know aj actually. So we have to determine bj and cj. Very good. So then we will solve for cj, bj in terms of, so here we have bj. We solve this equation, write the value for bj in terms of the remaining constants, which are aj's, cj's and hj's. Okay, and we'll put that value back in number 5. So this is the equation that we get for bj, which is 1 upon hj, the difference of a's minus hj by 3, 2cj plus cj plus 1. So this is what we get when we solve the equation 4 for bj in terms of aj, cj and hj, and we put them back in 5 to get a very long equation. But this is the equation hj minus 1 cj minus 1 plus 2 hj minus 1 plus hj cj plus hj cj plus 1 is equal to on the right hand side. So if you look at it on the left hand side, you have only hj's and cj's. On the right hand side, you have HJs and AJs. Okay. So which are the things that are unknown here? So for the moment, if you look at it very carefully, each such equation has only Cj minus 1, Cj and Cj plus 1. On the right, we have some quantities which are known to us. So we know AJs, we know HJs. On the left, we could think of it as some set of equations for C0, C1 up to Cn minus 1 and also for Cn, because that's the value that we would want to determine later on using the boundary conditions. So you have a linear system that we are going to get here, and we can solve this linear system using the number of equations, number of variables trick, and of course we will have to use some linear algebra here at this point. But let's see. Once you compute CJs here, you will go back to 6, which is there right on top of the slide, and solve for BJ. So computing CJ will give you the value for BJ, and then you go backwards to solve for DJ. That will give you the equation for SJs completely. Okay. So once we impose one of the boundary conditions, which could be either natural or clamped, then the above system can be solved for CJ. This is what we are claiming. And the proof of this statement we will not give here in complete detail, but what it does involve is some kind of linear algebra. I will once again bring your attention to this fact that the left hand side, where we are computing CJs, each equation will involve something in Cj minus 1, Cj and Cj plus 1. So when you start from j equal to 0, you will of course not have that C minus 1, because that C minus 1 doesn't exist. So you will have something for C0 and then something for C1. Then the next level you will have 0, 1 and 2, C0, C1, C2. At the next level you will have C1, C2, C3 and so on until the last moment where you will have only about Cn minus 1 and Cn, and you would not have the next Cn plus 1 term, of course. So what this gives you is that you will have a matrix on the left hand side whose entries in each row are non-zero only for 3 terms, maximum of 3 terms. For the first row you have non-zero entries, possibly non-zero entries for the first 2 terms, and in the last row you will have only 2 possible non-zero entries, and everywhere in between you will have 3 non-zero entries. So it will look like this, that you have the diagonal term, you have upper diagonal term which will of course not exist for the last row, and you have the lower diagonal term immediately below the diagonal, which will not contribute of course to the first row. So it will start from second row. The below the diagonal term will start from second row and will go all the way up to nth row. The entries which are above the diagonal, they will start from first row, but they will go only up to the n minus 1th row. And then you will have to claim that the particular matrix is invertible, so that you can bring the matrix to this side and solve for Cj in terms of the known constants. That's what we are going to have, which will come soon in linear algebra. And what we are going to do now is that we will solve this for an example. We will try an example and try to illustrate this whole system by means of an example. So what we have is that we will take this data for x comma e power x, and we have x equal to 0, 1, 2, 3. So we will have 1 cubic for 0, 1, another for 1, 2, and third cubic for 2, 3. So S0, S1, S2. Those are the cubics that we will have. N will have to be 3. H0, H1 and H2, these are all 1. Remember, Hi are Xi plus 1 minus Xi. So X1 minus X0, that is H0, which is 1. 1 minus 0. 2 minus 1 is 1. 3 minus 2 is 1. So we have that these are equally spaced nodes. A0 is 1 because that's the value at the point x equal to 0. A1 is E. A2 is E square and A3 is E cube. So we had 3 cubics and 4 into 3 is 12. We needed to compute 12 constants. Out of them, we have computed 4 constants already. We then have C0 is equal to 0. So why do we have this? This is because we have the formula. We are looking at this particular last equation, which should have been given some number perhaps, and these are the equations that we are going to solve. We have computed AJs, we know what are the HJs, so we have simply to compute for the CJs, and we do that. The answer is that C naught is 0 for C1, so we will have C naught plus 4C1 plus C2 equal to the right hand side. That's second equation, this is the third equation, and this is the fourth equation. Okay, so we have C1 plus 4, C2 plus C3 is something, 3 into something, and finally we have C3 equal to 0. If you were to write it in terms of a matrix, this is what we are going to have. So we will have the diagonal terms above the terms which are above the diagonal. They happen to start from 0, but they are there, and the terms which are below the diagonal. And this matrix is invertible. This is something that we have to notice. Or you may simply have that C0 is 0, C3 is 0, and you have to solve for C1 and C2. So you should look at only the middle 2 by 2 matrix, which is 4, 1, 1, 4, with whose determinant is 4 square minus 1 square, which is 15. That is invertible. So you can solve for C1 and C2 in terms of the matrix entries which are given on the right. So this system is solvable. It gives you C0 equal to 0, C3 equal to 0. C1 is this particular quantity which you have once you invert the matrix, either the 2 by 2 matrix or the 4 by 4 matrix, which is essentially the same. And C2 entry is this. So we have the full cubic spline, of course, because once you know C1 and C2, C0, C3 are known, you put them back and you can compute for B0, B1, B2, B3, D0, D1, D2, D3, and it will give you the cubic spline, where S0 is this particular term. Again, note that C0 is 0, so you will not have any entry for C0 there. We will have S1 given by this polynomial, S2 is this. So we have these three cubic polynomials, each on respectively 0, 1, 1, 2, and 2, 3. Now you may wonder why we are doing all this. So just to give you a trailer of the things which are going to come later, this, for instance, would enable you to compute the integral 0 to 3 e power x dx. Because you have approximated the function in a nice way, reasonably nice way, it will help you compute the integral from 0 to 3 e power x dx, simply because it's going to be approximately the same as the integral from 0 to 1 of S0 x dx plus 1 to 2 of S1 x dx plus 2 to 3 of S2 x dx. So this is what we get. And S0, S1, S2, these are all polynomials. So putting polynomials there and computing integrals of polynomials is something which is very easy than computing the integral of exponential. Of course, you may say that we can also compute integral of exponential, but this example illustrates why it is useful to have these cubic splines approximate your function, or why it is important to have something nice, but a polynomial type of thing which approximates your function in a nice way. So how does this approximation look like? This is how it looks like. It looks like a very nice curve. So y equal to sx, this is something which is in blue. It doesn't quite agree with the function value that we have. So we see that the function value from 1 to 2 is slightly above the spline that we have. From 2 to 3, it is below the spline, and after that it's going to go above. You may know that exponential function grows higher, goes to infinity faster than any polynomial, and similarly it's going to go to 0 very rapidly compared to any polynomial. So that's the behavior that we have at this point, and with this we stop. We will see in next lecture some more interesting things about cubic splines. We will also see the errors and some more properties of it. Thank you and see you soon.